Hello everyone. My name is Atsufumi Honda from Yokohama National University in Japan. Today, I will talk about singularities of space-like mean curvature 1 surfaces in Dojita 3 space. This is a joint work with Himemisato. As I mentioned in the introduction video, here I will explain what I want to discuss today. Minimal surfaces in Euclidean 3 space, R3, are related to surfaces of constant mean curvature 1, that is CMC1, surfaces in hyperbolic 3 space of sectional curvature -1 via Lawson correspondence. While the local properties are same, but their global behaviors are not the same. Globally, not the same. As a Lorentzian counterpart, there is also a Lawson type correspondence between space-like maximal surfaces in Lorentz-Minkowski 3 space R31 and space-like surfaces of constant mean curvature 1, that is space-like CMC1 surfaces in Dojita 3 space of sectional curvature 1. But unlike the Riemannian case, so it is known that complete ones must be trivial. Must be trivial. That is totally geodesic or totally umbilic. So we have to consider such the surface with singularities. In this talk, I will mainly deal with singularities of space-like CMC1 surfaces in Dojita 3 space. So this is the plan of my talk today. So this is the first part of my talk. In the first part, I will briefly review the known results on maximal surfaces or space-like CMC1 surfaces. And second part, I will explain our main result. So let's start. I will denote by R31 the Lorentz-Minkowski 3 space. That is, so this is the Lorentzian manifold with this flat Lorentz metric. Then an immersion F from smooth 2 manifold M into R31 is said to be space-like if so the ds square is Riemannian metric on M, where the ds square is the first fundamental form or induced metric of F. So then, space-like immersion is called a space-like maximal surface if the mean curvature h of the surface is identically 0. So the definition of maximal surfaces are highly similar to minimal surface in Euclidean 3 space, but their global properties are not the same. We can see such the result by this fact. So any geodesically complete maximal surface must be a space-like plane. Here, complete is, so this Riemannian manifold is complete. So by this fact, we can say that there must be singular points of non-planar maximal surfaces. So here, what is the definition of singular point? So let F be a smooth map defined on a smooth two manifold M. Then a point of the source manifold M is a singular point if F is not an immersion at P. That is, so the rank of the differential is 0 or 1. So I want to remark that the singular point by this definition is a point in the source manifold, not in the image. So then, Mehara Yamada in this paper, they introduced a notion of maximal surfaces with singularities, admissible singularities. So let M be a Riemann surface. Then a smooth map F is said to be a max space if the following two conditions hold. The first condition is there exists an open and dense subset of M such that the restriction map is a conformal maximal immersion. So almost everywhere F is a maximal surface. But the second condition is we can admit a kind of singularities, but very degenerate singularities we do not admit. So more precisely, there does not exist a point P such that the differential is a zero map. So the rank of the differential is not the zero on M. So in other words, the rank of the differential must be 1 for singular point P. So the second condition is a kind of restriction for singular point of maximal surface F. So this is a surface, a max face of revolution. So this is called maximal catenoid. This surface is a Lorentzian counterpart of usual catenoid in Euclidean 3 space. So the natural and fundamental question is, what singularities appears on max faces? We can say there does not exist a singular point of rank 0. rank 2. So then by this paper given by Fujimori, Sajumehara, and Yamada, they proved that generic singularities of Mach spaces are cuspidal edges, swallowtails, and cuspidal crosscap. So this is the figure of cuspidal edges, and this is the swallowtail, and this is the cuspidal crosscap. So here, generic means the space of Mach spaces equipped with compact open topology. So there exists an open and the subset of such the space of Mach spaces such that there is their singularities are only these three cants. Here I want to explain what is the definition of cuspidal edges, swallowtails, and cuspidal crosscaps. So let F be a smooth map between 2 and 3 manifold. Then F has a cuspidal edge at P if there exist local coordinate systems M2 and M3 such that locally the map F is given by in this local coordinate neighborhoods. So this map is said to be a standard form of cuspidal edge. In the words of map jumps, we can say more precisely. So let F1 and F2 be two smooth map jumps. Then F1 and F2 are said to be equivalent if there exists as diffeomorphism jump phi between source manifolds and diffeomorphism jump big phi between target manifold such that so this condition holds. This condition implies so this is a commutative diagram. So then F1 and F2 are same. So in the setting of map jumps. So F1 and F2 are same up to coordinate system. So then F defined source manifold M2 and target manifold M3 has cuspidal edge at P if F at P is the map jump F at P is equivalent to FCE the at P. So FCE is a map jump defined by this way. So FCE is this map jump. So similarly, we can define and swallowtails and cuspidal crosscap are P. So the standard swallowtail standard form is given by this, and standard form of cuspidal crosscap is given by this. So these figures implies the images of standard form. So These three kinds of singularities, capital H, swallowtails, and capital crosscap, consist of generic singularities of Mach spaces, but there exist non-generic singularities of Mach spaces. So geometrically, these two kinds of singularities have very important properties. So cone-like singularities, the standard form is this, so the circular cone. And fold singularities is this fold map. So these maximal surface Mach spaces with, so left one is cone-like singularities. So this is called catenoid, maximal catenoid, as said before. And this is a maximal helicoid. This surface have fold singularities. So, so this is the properties of such singularities. So the first one is called reflection principle. So if a Mach space admits generalized cone-like singularities, I will explain later what is the generalized one. Then the image of F has a point symmetry with respect to this cone-like singular point. So I want to remark that this is the image point of cone-like singularities. So this is proved by Kim and Yang in this paper. So the second one is related to fold singularities. So if a Mach space admits fold singularities, then the image of F can be extended analytically to time-like minimal surface. So here I want to explain what is time-like minimal surface. So the definition is very similar to space-like ones. An immersion F is called time-like if the induced metric is Lorentzian manifold. Then the time-like immersion is said to be time-like minimal surface if the mean curvature H is identically 0. So such the properties are proved by Gu, Chao Gu, and Kim Ko Shin Yang, and Fujimori, Kim Ko, Rasman Shin, Umehara, Yamada Yang. So this is maximal helicoid. So the singularities of maximal helicoids are fold singularities. So we can extend this surface. So we can extend it in this way. So this blue one, time-like minimal surface. In fact, we can extend one more time. Then we have fold shape of this maximal helicoid. So united figure is in fact usual catenoid in Euclidean space. So according to these facts, we can say cone-like singularities and fold singularities have big difference of Mach spaces geometrically. Other non-generic singularities I want to introduce today is cuspidal SK plus minus singularities. So, cuspidal SK singularity or CSK plus minus singularity for short is the standard form is given by this map. I want to remark that cuspidal S0 plus or S0 minus singularities coincides with cuspidal cross cap. So this map. So this is a cuspidal S1 minus singularity, and this is a cuspidal S1 plus singularities. So for even k, so cuspidal SK plus and cuspidal SK minus are A equivalent. CS2M plus is A equivalent to 2M minus. But for odd integer k, CS2M plus is not A equivalent to CS2M minus as in this figure. So so according to this fact, there is a restriction on singularities on Mach spaces. So if a Mach space admits a cuspidal SK plus minus singularity, then it must be cuspidal SK minus singularity. So, namely, there does not exist CSK plus singularities on Mach spaces or CSK plus minus where k is greater than or equal to 2 does not exist. So big restriction on singularities. So I have explained what kind of singularities appears on Mach spaces in Minkowski space. From now on, I will explain space like CMC1 surfaces. I will denote by R41 by Lorentz-Minkowski for space. Then the Dojita space is given by the quadric defined by this equation. So this manifold is Lorentzian space form. In fact, simply connected Lorentzian space of sectional curvature 1. So this space is called Dojita space, and Dojita space is diffeomorphic to this manifold S2 cross R. But this is very well known that there is a canonical isometric correspondence, so-called Lawson type correspondence between space-like maximal surface in Minkowski space and space-like CMC1 surfaces in Dojita space. So what is correspondence? So they are isometric to each other, but so the second fundamental form differs by this way. So we can we can we can image locally they are same, but so globally, so according to the Calabi theorem, we can expect there is also classification of complete ones. So that's the fact by proved by Akutagawa and Ramana-san independently. So the fact is complete space-like CMC1 surfaces in Dojita space must be totally umbilic and flat. So totally umbilic and flat implies that the surface must be space-like holosphere. So this is a kind of space-like planes in Minkowski space, space-like holosphere. So according to this fact, we can say there must be singular points of non-flat space-like CMC1 surfaces. So as in the case of Mach spaces, Fujimori defined a notion of CMC1 surfaces with admissible singularities called CMC1 phase. So the definition is very similar to Mach spaces. Similar to Mach spaces in R31. And similarly, we can consider the natural question is what kind of singularities of CMC1 surfaces? In the paper by Fujimori, Sajimehara, Yamada, as in the case of Mach spaces, they also proved the generic singularities must be capital H, swallowtails, and capital cross cap. So generic singularities of CMC1 phases are classified, and such the singularity are the same of generic singularities of Mach spaces. So I want to say what occurs of non-generic singularities. So I will explain explain about non-generic singularities of the CMC1 phases in the second part.